So let's take a look at number one here quick. It says the derivative is given, which is actually really friendly, right? We don't have to do the calculus work. They gave us the derivative, but we do have to understand how we're going to use the derivative to answer the question. And one of the things I want you to focus on here is showing the correct work and justification. So if I ask you to explain, why do you know that the original function is increasing? Well, what we're going to do is we're going to check to see when the derivative is greater than 0. This is your justification. You don't need to write any more than just when f prime is 0, or when f prime is greater than 0, my function is increasing. So it's a simple step, and if you write it, you're good to go. Well, what do we need to do to first figure out when it's increasing? That's where the critical points come in. And the critical points are where the derivative is equal to 0. So, since they already gave me the derivative, I'm just going to set the derivative equal to 0. And then it's just algebra. So I notice that each one of these have a factor of 3x in common. So if I factor a 3x out, you don't even have to show me each one equaling its own 0. You could just tell me the answers from there, but if you want to, you get x equals 0, and you get x equals positive 4. So those are my critical points. It's basically how we always start off any question with using the derivative is find the critical points, and then we have to use the sign chart to test the critical points. Now, we should always label this as f prime of x. The reason why is that tells us what we're using. We're using the derivative to figure out the signs between the critical points. I know the derivative is 0. If I plug in 0, the derivative is 0 because that's what I found, and same thing with 4. So I know that these are 0, but what about to the left of 0? Now here you could pick a number like negative 1, and you could plug it in here. If I plug negative 1 in and I square it and times it by 3, I'll get a positive. If I take negative 1 and times it by negative 12, I'll get a positive, and a positive plus a positive ends up being positive. Okay? You don't have to show any work for checking the sign. And a lot of my kids last hour were kind of surprised by that. They're like, what? I don't have to show work? Not for this part. So then I'm going to pick 1, right? 1 is a really friendly number between 0 and 4. If I plug 1 in here, I end up with a positive number. If I do negative 12 times 1, I get a negative. So then a positive and a negative add together to give me, well, I should be careful on that. This one, since we're not multiplying here, we're just adding. Which, by the way, I would actually do this. I would use this form of the derivative instead of this one. In my mind, it's easier. If you plug 1 in here, you get a positive. And if you plug 1 in here, you get a negative, and a positive times a negative is negative. Right? But any form of the derivative you can plug numbers into to check. And then if I pick a number greater than 4, I like to actually pick infinity. I mean, you could pick 5. I like to think of infinity because then I'm just dealing with signs. If I plug in a positive infinity here, it's going to be positive. If I plug a positive infinity in here, it'll be positive, and a positive times a positive is positive. So then the question is, when is the function increasing? Well, it's increasing whenever the derivative is greater than 0. Another way to say that is wherever the function is positive. So in this case, we are increasing from negative infinity all the way up until 0. And then from 4 all the way up to positive infinity. Now, some of you were working on Delta Math, and when you check their answers, they did this. The way they would write this is they would say x is less than 0, and then they would say when x is greater than 4. And they put the equal to line underneath it. I actually don't agree with that part of their answer. The reason why is because at 0, at 4, your derivative is 0. 0 isn't positive or negative, so the function is actually stopped right here. This is where the function is stopped, and it's not increasing or decreasing. So I double checked it, and if you put it as just a less than or equal to sign, they accepted that answer as well. Now, the other way you could write that is this way. You could say from negative infinity to 0, and then you would go from 4 to infinity. So Delta Math accepted any of these versions. Personally, I like this one. Okay? And the reason why there's soft brackets here and not hard brackets on the 0 and the 4 is because at 0 and at 4, the derivative is 0. So hopefully you're pretty comfortable on that. I wanted to give you a problem like this where they already give you the derivative. So be careful. Don't take the derivative of the derivative, because then we're dealing with the second derivative. So you really have to just pay attention to the notation here. All right. And then this one. Classify. So classify means tell me, are they a max, a min, or is it neither? So classify the critical points, and this should be plural, because I believe there might be more than one, but classify the critical points. Well, what are critical points? Critical points are where the derivative is equal to 0, or the derivative does not exist. And the reason why I picked this problem is you'll see in just a second, but we're going to do basically the same work we did above. I have to take the derivative of the function, and then I have to find the zeros. And this is the interesting part. The first thing is I don't like the way that this square root is written to take the derivative of, so I'm going to just rewrite it as x plus 2 to the 1/2. Now notice that's just algebraic, so it's not a derivative. And now I'll take the derivative. So the 1/2 comes down, take 1 away. And then I'm going to do this just so we don't forget. There should be, we're checking the chain rule because there is that inside function. So I'm taking the derivative of the inside, which is 1. And that doesn't really change anything. So I'm okay there. And then we're going to try to find the critical point. So I'm going to set it equal to 0. But anytime you have a constant out front, the 1/2, and it's equal to 0, I can get rid of that constant by just timesing both sides by 2, right? Or 2 over 1, because that'll reduce this constant out. And timesing the left side by 2 is still 0, so it doesn't really change it. And then notice what happens here. I'm going to rewrite this as using the negative exponent putting it in the denominator, because I can then set up a fraction equaling a fraction, and we can cross multiply. And when you cross multiply, you actually end up with 1 times 1 equals 1, and 0 times this whole thing, which is 0. You end up with a false expression, which means that there are no spots where the derivative is equal to 0. But is there a spot where the derivative is undefined? And that's where something we kind of notice. If you look at any one of these forms right here, they're still the derivatives. And the only time that it will be undefined is when x is equal to -2. If I plug a -2 in here, what's going to happen is I'll get a 0, and the square root of 0 is 0, so I'll get 1 over 0, which is undefined. So at x equals 2 is a critical point. Excuse me, x equals -2, because the derivative does not exist. And we really haven't seen that yet. That's part of the reason why I put this one up. So my thoughts were I wanted you to try this and get to an expression like this where you're thinking, well, wait a minute, what happens? Then we got to go back to if the derivative doesn't equal 0, where does it not exist? And that's our critical point. But you're going to notice something with this example. Notice how the critical point is actually still the end point. Well, in that case, since we have endpoints, we do have to check those endpoints as well to see are the endpoints a max or a min? So I'm going to create a table, and since the critical point is the same as the endpoint, we only have to check two things. Now here's the part that we've got to check. We're looking for which of these endpoints could be an absolute maximum or minimum of the function. Now notice, since we don't have any critical points to really check, we're not doing a sign chart, we're not using the derivative, I'm going to just check the outputs. So this is the original function f. And I'm just going to plug in -2, which that's really friendly. The square root of 0 tells me when x is -2, its output is 0. And then this one we get the square root of 6. The square root of 6 is bigger than 0. So I now have a conclusion. We have an absolute minimum of 0 at x equals -2, because it's the lowest point of this function. And by the way, this function is continuous. If we were to look at the graph, you could kind of confirm that. So that's why I know that this is the lowest point of all of it, and then here's the highest point. So then we have an absolute max of square root of 6. And then where does it occur? At 4. It's titled Extreme Value Theorem, and it just says if a function is continuous on a closed interval from a to b. So let's just look at these red graphs quick and look at from a to b. You can see that this one is continuous from left to right, and it has filled in circles, so it is a closed interval. Same thing here and here. They're all continuous on a closed interval. So the hypothesis checks off. Well, if that's true, then my conclusion says the function has to have a maximum and minimum on that value. So let's just confirm that that's true. And if you look at it, right here is the absolute max, right? And then right here, because the filled in circle, that is the absolute min. And notice, it does have a max and a min because it's continuous on a closed interval. Well, right here, the endpoint is the minimum, and the endpoint over here is a maximum. And then over here, you can see one of the endpoints is the minimum, and somewhere up here is the maximum. So I just wanted you to show this picture to show you that maximums can occur or minimums can occur at endpoints, and sometimes it's only the endpoints, or sometimes the function goes up and then down, and a maximum is somewhere on the function or not at the endpoint. So it's just the difference of what your function looks like, and that's the importance. If we ever have an interval, we have to check the endpoints. So notice how they gave us the interval from a to b. If I had a real function, I took the derivative, here's where a critical point would be. But if I didn't check the endpoints, I would only think there was a maximum. I would miss the minimum value because you have to check the endpoints. And that's basically what the extreme value theorem is saying. Okay, now don't write this one either. There's a handful of things we're not going to write today, just to give you a little exposure. So what if I gave you a graph like this? Identify all extrema or extreme values. All right, if I look through this, well, this is an endpoint. It's a minimum because it's filled in, but it's a special kind of minimum. Right? It's a local minimum because it's the lowest of all the points around it. Then if I go here, this one is the absolute lowest point on the graph. So when it's an absolute min. If I look at this endpoint, it's not the highest, it's not the lowest, but of all the points near it, it's a local max. And this last one, we're saving the best for last. This is where kids get a little bit confused. Okay, now notice, as I go closer and closer to this graph from the left and from the right, I'm getting closer to the output of 2. But I'm never ever going to reach 2. I'm going to get closer and closer and closer. And since I'm always getting closer to 2, this point is not defined. So this is not this is a neither point. It is not a maximum. Okay? Even though these points over here are definitely higher than this point, it's not an absolute max because for every spot you get closer to 2, you can always go closer to 2. Right? So just be careful there. Is if it's undefined, you have to be, you cannot tell me the exact location of this point because we can always get closer and closer and closer, but we'll never reach that number. So think of this. What about the slopes of the tangent lines at these values here, here, even here? Well, another way to say that is the derivatives. What are true about the derivatives at every single point? They don't exist because the slope on the right is not equal to the slope on the left. So these are critical points, but this is an example like we saw in the second warm-up today. The derivative does not exist. And same thing here. The derivative does not exist because the slope on the left is negative and the slope on the right is positive, so therefore the derivative doesn't exist. And then here, officially, the derivatives don't exist at endpoints, and the reason why is because there is no slope on the left or the right. So this is a visual reason why when we look for critical points, yes, this was an absolute minimum, it's a critical point, the derivative does not have to exist. So when we check critical points, the derivative is 0 or it does not exist, and this is just a graphical representation of that. Okay, it's up to you if you want to write this. These were in our notes from Monday, Tuesday, but I just want to go through really quick because I like now that you had a chance to practice it, I like the summarization piece of this slide. Okay, I can use the derivative, f prime of x, to determine when a function has critical points, max, mins, increasing, decreasing. So what if you had a test question and it said, find the critical points. And then it says justify. What work do you have to write down to justify these points? Well, all you have to do to justify where critical points exist, my smartboard decided to act all funky for a second. Try this again. There we go. So if I ask you to justify, all you have to do is how do we know critical points exist? You tell me that the derivative is equal to 0 or the derivative does not exist. That's all you need to write in terms of a justification. You don't have to write long sentences, and we actually encourage you not to, right? Shorter is better. What about if I asked you to determine if there's a maximum? Well, all you have to do is tell me that the derivative changes signs from increasing to decreasing, from positive to negative. Now, I will point out one thing, and I want you to be aware of this. I don't fully agree with it, but I'm not on the AP grading board. You need to write this phrase out in words in order to justify why you have a maximum. You cannot just show a sign chart. And it's unfortunate, but let's say that you had a point A and it switched from positive to negative. Showing this work is only for you. They actually aren't even going to look at this work. But what you need to do is you need to write out this phrase which summarizes that sign chart. So sign charts are not official justifications. It's only work for you. You have to write it out in words as to why the maximum occurs. And I know that doesn't seem right, but that's the way the AP board is emphasizing it. So how do I know if a minimum exists? The derivative changes signs from a decreasing function to an increasing function, from negative to positive, right? So I always think of this, maximum went from positive to negative. You can kind of see that there's a maximum here. And if I had a different point and I went from a decreasing to increasing function, you can see that if I have decreasing slopes to increasing slopes, you can tell that there's a minimum that's going to be right there. So the green is the justification that you have to have. All right, how do I know if a function is increasing? Well, this one is really quick. All you have to do is say that the derivative is positive. It's greater than 0, and that's it. That's your justification. A lot of times you get 1 point on an AP free response question just for that. And then how do we know if we're decreasing? Because the derivative is negative. Okay. So again, the sign chart helps us interpret, but the green justifications is what we're looking for you to write down. Okay, if you didn't get a chance to write all that down, you want to, it'll be posted on our Schoology site here in the written filled out notes. Okay, this problem we're going to do in our calculator. So I want you to grab your calculator if you're using your computer one or if you got a TI-84 in front of you. I'd like you to pull that up. And we're going to kind of work through this together here. So again, don't write, but applied motion, calculator question. When you come across a problem like this, you don't have to show any work. It's all in your calculator. You might be asked to justify, but you don't have to show any work there. I gotta fix this. All right, so let's read this and just kind of, I'll show you how I would interpret this. So it says a particle's displacement. That word displacement is the same as the position. And the position is given by the function x of t. And then, yeah, it's a funkier equation, which is why this is going to be our calculator one. And then it's given to me over the interval from 0 to pi. And remember, these intervals, it's not a point. These are your x's. So another way you could write this is like this. That's what this interprets. So then they're saying, when is the particle stopped? Well, if I asked you to justify, here's the only thing you need to know. Well, the particle is stopped when the velocity or the derivative of position is equal to 0. So I'm just going to take the derivative of this and I want to figure out where it's equal to 0. And this is all calculator work. If they say derivative, you do not have to take this derivative by hand if you're using your calculator. Okay, so I can make this work the way I want it to. Perfect. Okay, so everybody grab your calculator, go to y equals, and we're going to type this function in. E, the second ln, and then we've got sine of x squared. Okay, and instead of t, we're going to use x, just because that's our computer. Now, we're also going to do another thing, because I don't want the original function. I want to use the derivative. And by the way, let me just show you this quick. Let's set our window. Our window was from 0 to pi. Okay, my x was from 0 to pi. And then I think I'm okay with a negative 10 to 10 graph here. And let's go ahead and just hit graph right now. This is the original function. And you can see it has maximums, it has a minimum and another maximum. And you could find the maximum, minimum, and the other maximum using non-calculus, but this is a calculus class, so we're going to focus on the derivative equation and not this blue regular position equation. So let's go back to y equals. And what I want to do is I want to graph the derivative of this function. And Mr. Waffler showed us a way to do this in the video. If you didn't watch the video, this will be new to you. So, and I learned something from one of my students last hour that I'll show you. If you go to math, we want to graph the derivative. So hit math 8. And by the way, I don't know if I said this. I'm going to go back. You have to be in y2. So click your cursor down to y2 and then go math option 8 and hit enter. And what that does is that gives us this derivative. So I want to put d dx. And here's the spot where my student showed me. Instead of going to the vars button, if you go alpha trace, so alpha calc, look at what that does. It actually activates your y1, y2, the y vars. So I want to take the derivative of y1, so do alpha trace and select option 1. That's y1. That's taking this whole equation and putting it in there. And then, as Mr. Loeffler said, x equals, we don't want to put a value, we want the whole function. So that's what should go into your y2. It's saying I'm going to take the derivative of whatever equation was in y1 for all x's. Okay, now hit graph. Once you have that in there, go ahead and hit graph. By the way, I'm recording this, so when class is done, if you missed something, you'll be able to go back and watch this part of the video if you need it. But look at the red function now. This red function is the derivative. So I want to figure out when is the particle stopped, or when does the derivative equal 0. So I'm looking at my red function, and I want to find all the spots where the red function crosses the x-axis, because that's a 0 derivative. All right, so I've got 3 spots here, 1, 2, 3. So how do we find the zeros? Well, that's second calc, and this is the same work you did in Algebra 1, Algebra 2, and pre-calc, so hopefully you're really good at finding zeros. But notice when I did that, it put me on the blue equation. I have to press up or down, it doesn't matter, to jump to the red derivative equation. So you always want to make sure you know what function you're on. Okay, so then it says left bound. Well, I have my cursor right at the 0 I want to find, so I have to go to the left of that a couple of spots and hit enter. And then for the right bound, I have to be to the right of the 0 that I want to find, so I'm going to go past that 0 and hit enter. And there's my first 0. Okay. I have this written down, so let's find all 3 of them quick, and then I'll write it down on paper. So there's the first 0. Okay. If you didn't catch that, I'm going to do it again for this red 0 right here, so kind of watch. I'm going to hit second calc, go to 0, and then it put me on the first equation. I have to be on the red equation. Now I'm going to go to the left bound. And if I want to be to the left of this 0, here's roughly where that 0 is. So I want to be to the left of that. So I'm going to hit the left arrow a couple of times. And then it says right bound. So now I have to be to the right of that 0. So here's where the 0 roughly is. I'm going to go to the right of that a little bit. Hit enter, and it's going to find the 0 in between. Okay, and then the last 0 is this point where my cursor is at. So I'm going to do the same thing. Second calc. Oh, by the way, I would record this 0 down. So then I go second calc, 0, and oops. Notice how it's taking me on the blue one. I don't want to be that, so I'm going to press up so I'm on the red function. And then I want to be to the left of this 0, which that's fine. And then to the right of it is below the x-axis this time. That's fine. And there we go. Okay. So that's finding the zeros, which anytime the derivative is stopped, the derivative, or anytime the particle is stopped, the derivative is 0. So I'm just going to record my answers. Now you'll notice I have these pre-written down. We don't really want to round yet because I may be using these answers later on. And you don't want to round until you have your final answer. So my advice is just take all the decimals that they give you, and then you know you're always in good shape. All right, so here's my justification. This is when the particle is stopped. My justification is I found when the derivative is equal to 0. All right, the second part of this question asks, when is the particle's displacement the greatest? Well, remember, another word for displacement is position, and another word for greatest is the maximum. So I have to figure out, when does this have a maximum value? Well, notice, I already have the critical points right here. And then I have my endpoints right here. So what I'm officially going to do, now notice this as well. I don't have to, I'm going to take the endpoints, and then I'm going to take all the critical points, and my goal is to figure out, of those, which one is the maximum position. So we do have to test all the points, but we don't have to show any work for this because our calculator is going to figure this out. Now you'll think of this, or you might be asking yourself, why aren't we making a sign chart here? Well, we don't need to, for a couple reasons. One, if I just test the outputs, I can tell whichever one has the highest output, that will be an absolute maximum. The other reason why is look at our graph. Okay, look at the blue graph. I only have 2 maximum points. So really, I don't have to check the endpoint at 0, the endpoint at pi, or this middle 0 right here. Okay, I just want to figure out, of these 2 blue maximums, I'm wondering one of these is going to be the absolute max, or maybe they both are. Okay, so what I need to do now is I need to find the values of the original function. So you could do this if you want. You could go and turn off the derivative. So notice how I just highlighted the equal sign and then I hit enter. And when I do that, it unhighlights it. And then it just graphs the original function. But I actually want to make a connection to the derivative with our answer here. So I'm going to leave that on. Okay, so I want to find the original value of all of these. So let's go second calc and look at your first option. It says value. So if I hit enter, I want to find out when x is equal to 0. So just type in 0 and hit enter. And notice I'm on the blue function because I want to find the original function's value. So that's equal to 1. All right? And then I'm going to check all of these. So we'll do that pretty quick. My advice would be have just a piece of paper down and write these down. So go second calc. Now we're going to do value, but this time I want the decimal 1.253, and it is a good idea to type in the entire decimal that they give you. Okay, that's your entire zero from above. Hit enter. So notice here's your maximum, 2.71882818. Okay, and then we're going to do the same thing for the other points. I have these pre-written down, so I'm going to fill in this table in a second. But I wanted you to look at one thing. Actually, you know what? I'll do this in a second. Let's find the other values. So now do the 2.17. Hit enter. And you can see that that is not as high as the other one, so that's a minimum. But is this a better question might be, where is it the actual minimum? Is this point lower than the point at 0? Yes. Is it lower than the point at pi? I'm not sure. I'm guessing yes, but I can't be certain until I check. All right, and then let's do the other maximum. You can see we're at 2.7182818. That was the exact same thing as the other maximum. So now we have two spots where the displacement is the greatest. And then let's do the last one at pi. So second calc, option 1, and then enter pi. And that shows me my end point right there. Okay, so how would I basically finish this work? I would record all those outputs of the original function. And then officially to answer this question, when is the displacement the greatest? Both of these. So we have two absolute maximums. Because they're both exactly the same. So what is the max? The max is your output. Where does it occur? The where is the x values. Okay. But what else could we conclude? This is kind of an interesting piece. Well, what else can we conclude if looking at these outputs? This critical point up here, which was a minimum, is the absolute min, so we can include that again. The end point is a lower spot right over here on the blue graph. That's a local min. And then we're at pi, that's another low spot. So that's a local min as well. So we can make other conclusions. We could also determine where the function is increasing and decreasing. So we're taking a lot away from this problem. Let's look at this. Okay, now I could make a sign chart using all this information and test, but if I have the red graph, which is the derivative, look at what happens. When is the derivative greater than 0? Well, it's greater than 0 anytime it's above the x-axis. And again, we're looking at the derivative graph here. So notice if I wanted to, I could say from 0 to the maximum, it's increasing. And then from the minimum to the other maximum, it's increasing. So then where would the function be decreasing? It's decreasing when its derivative is negative. And the red graph is the derivative. It's below the x-axis. So I could quickly identify the points at which it's decreasing as well. Now again, we are doing this work with the thought that we're never going to look back at the original function. Okay? So here's the way my brain works. Graphically, if my derivative is greater than 0, then my function is increasing on those intervals. If my derivative is less than 0, so it's below the x-axis, then the function is decreasing. And just by doing this, watch how we can interpret this now. Okay, if the red graph is the derivative, I'm above the x-axis here. This point is a critical point, and then I'm below. So my slopes go from positive to negative, which we know there's a max. That's what we just found right here. And then if I go from negative to 0 to positive, this point right here is a minimum of the original blue function. And same thing here. I go from positive to negative. This point right here is the other absolute max. So we will get more practice with the calculator. I just wanted to give you all okay, so we're going to do this one. This is a no calculator problem. And I just want, it's an AP style question. You don't have to write the A, B, and C here for the choices, but what are the values of x for which the function f of x is increasing? So here's what I would recommend if you were doing this on a test, my test or an actual AP test. When you see the word increasing, you want to make a connection to calculus. So we're thinking, what do we know about the derivative if it's increasing? It has to be positive. And that tells you we need to take the derivative and then do a sign chart. And then that sign chart will tell us when the derivative is positive or negative, and we can answer the question. So the nice thing about this problem is it's the same work and same style of problem that we did the last couple of days. The part that makes it challenging is the calculus side of, ooh, now we've got a more challenging function, which is a product rule. So remember how we said basically everything that you're going to use or learn in calculus you're going to use again, and this is the case. So if I'm going to take the derivative of f of x, I have to use the product rule. And I want you to, I'm going to let you guys do this for a second once I get things set up. Go ahead and write out the product rule for these two pieces. So I'll give you a chance to get caught up in writing, and then I want you to find the derivative using the product rule. So we take u, and the derivative of u is x. X squared is just 2x. The derivative of v, e to the negative x, well, the derivative of e to the negative x is itself, but then we have the chain rule. So I have to take the derivative of the negative x, which is -1, but instead of doing times the -1 at the end, I just put the negative out in front. So once we have the derivatives of the first and the second, we're going to apply the chain rule. So the derivative of the first is 2x times the original second. That's the blue part. And then we've got x squared minus 3. So the first times the derivative of the second. And notice how I didn't like distribute or anything. I'm just going to leave it because I need to figure out when this derivative is equal to 0. Now here's kind of the new part, or I can't say new, but the part that students struggle with. It's the solving part after they take the derivative. That's where the challenge, I think, comes. So let me show you what I notice here. I can't just solve this for 0 the way it is, but I do notice that they each have an e to the negative x in common. So I'm going to factor that out, and I'm actually going to factor it out so this negative here comes out with it. So, oops, I'm going to take a negative e to the negative x away from both pieces. Right? When I do that, this 2x, if I take a negative away from it, it's going to be negative 2x. And then since I'm taking the negative e to the negative x out, we're left with just x squared minus 3. Okay? Now that looks not awesome, but it actually helps us. We can do our zero product property. This first factor could be equal to 0, and then the trinomial. But I'm going to rewrite the order of this trinomial so it just looks better. Because then I can quickly factor, and you don't even have to show the work here. You know you're going to get x equals 3 and x equals negative 1. Okay, so that's the friendly part. Then we come over here. Now, if you understand what's going on here, you know this answer doesn't exist. Because e to the x, regardless if it's positive or negative, will never equal 0. This function is always positive, but then because of this negative, it's always going to be negative, which means it'll never equal 0. But if you didn't see that, algebraically, you could still solve, and you would find and justify why. So if I get rid of the negative over here, if I divide by a negative 1, I'm left with this. And then pre-calculus wise, how do I get rid of base e? We take the natural log of both sides. And the ln and the e go away, so it says negative x is equal to ln of 0. Well, the natural log cannot equal 0, so it doesn't exist, which means we don't care about this work right here, because it's not going to determine when this is 0, which means I just have 2 critical points. Okay. So I think this is where you're going to struggle a little bit, is once you take the derivative, solving that piece. And it's all fair game, everything you learn from pre-calc. So we basically, unfortunately, can't go over every single type of problem. You're just going to have to experience it and ask questions when you need to. Okay, so now I'm going to do my critical points. I'm going to check the derivative, the sign of the derivative between those points. Now, since we know that this part right here, it doesn't matter what x is, that's always going to be positive, and then this negative, this part will always be negative. So the only part I'm really looking at is this part to determine the sign, knowing that this will always be negative. So you could keep this value. I actually like to look at the factored version of this to help me out. Okay, so I'm going to test the point. A friendly point to test past negative 1 is negative 2. If I plug in negative 2 here, I get a negative, and I get a negative, and a negative times a negative is a positive. But then we know that this part will always end up being negative because of this piece right here. So a negative times a negative times a negative, that's an odd amount of negatives. So that portion will be negative. If you don't like this part of doing it in your head, you could literally plug negative 2 into all those and simplify, but we don't have to. We don't want to use that time. So what if I plug 0 in? Okay, 0 here will be a negative, 0 here will be a positive, and this will always be negative regardless of what the x is because of that sign right there. So negative times a positive, even amount of negatives is a positive. And then I can check any number past 3, so let's check 4. Okay. If I plug 4 in, 4 minus 3 is positive 1. If I plug 4 in here, I get a positive, and this answer will always be negative. So now I know when my function is increasing. It's increasing from negative 1 to 3 because that's where the positive will be positive derivative will be. So I could write it this way or answer D. So tonight's homework, you are going to have some pieces where You have to use the product rule. Maybe it's a quotient rule. Maybe it's just a chain rule. Okay, the last slides I don't want you to write down. These are really quick, and we're going to go through them pretty fast. So don't write these down, but let's just look. If I gave you a graph like this, and I asked you to find when is the function increasing, what are you going to do? You're going to say, I need to know when the derivative is greater than 0. Well, look at it. It tells us that this is the graph of the derivative. So I have to understand what graph I'm looking at, which means here are my critical points, and anything above this line is where the derivative is greater than 0. So it's increasing from here to here because that's where we have a positive derivative. So to answer this question, if I go from negative infinity to 0, and I could put the union symbol or I could just leave it blank, it doesn't matter. And then from 4 to 0, this is where the function is increasing. So where would it be decreasing? It'd be decreasing when the derivative is less than 0. Okay, so anytime you're below here, that's when your derivative. All right, next one. This is basically the same question. It's just a different graph. So where's the function increasing? Well, it's increasing when the derivative is equal to 0. Notice they don't directly tell me, but it's written right here. This is the graph of the derivative. So when is the derivative greater than 0? Oops, I put the wrong side. Greater than 0. Anytime we're above this. Now, when we write our values, we're dealing with the x values. Okay, so it's increasing from -6 to -2. From here to here is positive, and then again from here to here, so this would be 2, 3, 4, 5. Okay, and notice, how do we justify their answer? Right there, that's my justification. All you need to do is say, this is how I know the derivative is greater than 0. Okay, we're going to skip this one, and this is our last one. Okay, so what does this look like on a table? Well, find where the function is. That was written incorrectly. Find where the function is increasing. Now notice, what do they give us? This is the graph of the derivative, or it's the table of the derivative. So I know I have 2 critical points right here. And then where is f increasing? F is increasing anytime I have positive slopes. Well, look at those slopes are positive. If I wanted to, I could draw a sign chart here. And at x equals 0, I've got a 0 slope. At x equals 4, I have a 0 slope. And then reading this chart, I've got positive derivatives to the left of 0. I've got negative derivatives to the right of 0. And then to the right of 4, I've got positives. So you can look at this the same way we do graphs. But you have to be careful. We only have the values from -3 to 6. We don't know anything else about this. So when you write your interval, we have to start at -3 and we're going to go until 0. Increasing from -3 to 0 because I got positive slopes. And then we're going to go from 4 to 6. I can't say more because I don't know anything past the table. You can only use the information in the table. Right? Last piece. What if I gave you this? And this is a big understanding with tables, and they will test you on this in the AP test. So give me just a minute extra here. Okay, so this is my graph of the derivative. Notice, what do I have? I've got a critical point. And I have positive values to the right, and then I've got negative, negative, positive, positive, but I don't have any zeros here. We cannot conclude and make up values in between. We know that if it's continuous, there's going to be a 0, but we don't know where. So in this case, we cannot conclude anything because we're not sure where the second sign change would happen. So basically, whenever you see values in a table, you can only take the values that are given. You cannot determine what's happening in between. Because I don't know at 4.7, I don't know if that's going to be positive or negative. We just don't know, and you cannot conclude that. All right. So homework tonight, this is where it's mislabeled. If your homework tonight is on AP Classroom, it officially says quiz 5.1. It shouldn't have said that, but it does. Show your work and submit that written work to Schoology. I'll be in my office hours today from 1 to 2. If you guys have any questions, please stop on by. I can help you with calculator stuff or anything else.